Imagine drifting toward a black hole 4.3 million times the mass of the Sun. Around it, superheated gas races through a brilliant accretion disk. Gravity bends that light into glowing arcs above and below the darkness. What you see at the center is not a surface. It is a shadow around a region from which no light can return. Ahead lies the event horizon, the invisible point of no return. To a distant observer, your image would slow and fade. But on your own clock, the fall continues. Cross that boundary, and every future path leads inward. This is what happens when you fall into a black hole. Before the fall, you must choose your black hole. The smaller one may be more dangerous. A stellar mass black hole can have an event horizon only tens of kilometers wide. Near it, gravity changes sharply from your head to your feet. That tidal force could tear you apart before you ever cross the horizon. A supermassive black hole is different. Its enormous horizon makes the tidal gradient far gentler. You could cross without noticing a boundary, so we choose a giant 4.3 million times the Sun's mass. The journey begins nearly 640 million kilometers from the horizon. At first, the black hole appears almost motionless, but the light around it is alive. Hot gas races through the accretion flow, while magnetic turbulence triggers unpredictable flares. That glowing matter, not the black hole itself, is what reveals the darkness. A direct path through the disk would be fatal. Its million-degree plasma could destroy us long before the horizon. So in this idealized journey, we descend from above, avoiding the brightest material. No engine pushes us now. Gravity accelerates the fall. The disk spreads across the sky. Background stars begin to curve, while light ahead grows brighter and whiter. The shadow becomes larger than the invisible horizon it conceals. We are still outside, but space-time is already reshaping everything we see. Near a black hole, your eyes can no longer trust direction. Light follows the curvature of space-time. Stars hidden behind the darkness bend around it, appearing as arcs and duplicated images. The accretion flow becomes even stranger. Its far side appears above the shadow, while another image folds beneath it. These are not separate disks, but different paths taken by light from the same matter. Closer still, some photons orbit the black hole one or more times before escaping toward you. Their repeated images compress into thin photon rings. With every moment, the outside universe twists into arcs, loops, and layered regions of light. The horizon remains invisible, but the geometry of light is telling us it is close. The same fall creates two radically different stories of time. To an observer far away, our descent appears to slow. Each new image takes longer to escape the deepening gravity. Our signals stretch toward red, becoming dimmer and increasingly delayed. We seem to hover just above the horizon, but we do not remain there as a bright, frozen image. Our last visible light fades into darkness. For us, nothing freezes. Our clock keeps ticking normally, and the horizon arrives in finite time. There is no wall, flash, or sudden impact to mark it. These views do not contradict each other. They are different measurements along different paths through curved spacetime. Outside, our image disappears. For us, the point of no return is only moments away. We cross the event horizon, and nothing announces it. There is no wall, flash, or sudden impact. For a supermassive black hole this large, tidal forces at the horizon may still be gentle enough to survive. Our clock keeps ticking. Local physics feels normal. But one fact has changed forever. Outside the horizon, some future paths could lead away. Inside, every possible future carries us deeper. Even light aimed outward cannot escape. The universe we left behind is still visible, distorted and compressed into a shrinking region of sky. But no signal we send can ever return. Space itself carries everything inward. In this simplified model, the singularity now lies in our future, as unavoidable as tomorrow. And deeper inside, the calm ends as tidal gravity begins to tear everything apart. Deeper inside, gravity no longer pulls every part of us equally. The side nearer the center accelerates faster than the side behind it. That difference is tidal force. It stretches everything along the fall while squeezing it from both sides. At first, the deformation is subtle. Then, it grows violently. No body, machine, or material structure can remain intact. This is spaghettification. It is not caused by a visible object. It is space-time changing too sharply from one point to the next. For this supermassive black hole, the horizon was survivable. Deeper inside, destruction becomes unavoidable. The remains form a long, narrowing stream as the outside universe contracts into a distorted patch of light. In this simplified model, only microseconds separate destruction from the singularity. There, general relativity predicts infinite curvature, and our physics can no longer tell us what truly happens. During the final microseconds, our classical journey reaches its last prediction. General relativity calls this boundary a singularity. For a non-rotating black hole, it is not a glowing object waiting at the center. Inside the horizon, it is an unavoidable boundary in every possible future. As the classical radius approaches zero, space-time curvature grows without limit, and every remaining path ends. But infinity is not an answer. It is a warning that the theory has been pushed beyond where it can describe nature. Here, relativity must somehow meet quantum physics, yet we do not possess a complete, experimentally confirmed theory of quantum gravity. Quantum effects may replace the singularity with something finite, but we do not know. Wormholes, cosmic bounces, and new universes remain speculation, not established fact. No signal can return to tell us what truly happens. At the heart of a black hole